of differential geometry class. Today we are going to deal about the Gauss map. So before starting the Gauss map, we want to study what is the definition of such a map. So here is the definition. Let S be an oriented end surface. S be an oriented end surface that is a end surface S together with a smooth unit normal vector field N on S. That is an end surface with a smooth unit normal vector field. Now the function, we are defining a function. Now the function n from S to Rn plus 1 associated with the vector field this n vector field n by n of p is equal to p comma n of p. So we are taking this associative function n of p comma p belongs to S. Actually map S into the unit n sphere into the unit n sphere Sn, which is contained in Rn plus 1. Now since norm of your n of p, we are taking only the unit normal, so norm of n of p should be equal to 1 for all p belongs to S. Thus to each oriented end surface S is a smooth map. Thus to each oriented end surface S is a smooth map n from S to Sn called the Gauss map. So this is the official definition of what's a Gauss map. So first of all, we are having a surface. Let us have a picturization in R2. So in R2 means I want to have an end surface, means it should be a curve, something like this. So this is my surface in R2. Now taking a point here, let the point be P. Now here we are defining a normal. So this is my n of P. We have said that this should be an oriented end surface. So in each point I am giving the direction as this direction. Now this is n of p and what we are considering is the unit normal. So norm of this should be equal to 1. So I can shift this to my origin. So this is my origin. So I'm shifting that to the origin means see, suppose I'm shifting this to the origin. So if I'm shifting this means again I will get unit 1 only. So this unit normal I am shifting here. Okay, this I have shifted to here. So like that, if I am having so many vectors here means exactly I will get it as I will get as a circle, right? So I will get a circle like this. Only thing is that it should pass through like this. Okay, now for each normal I can place that normal in the origin like the circle. Now this is my n of p. That means this is my Gauss map. So this is the Gauss map of a one surface. So what does this means? It is the Gauss map of a one surface in R2. So this is the definition of Gauss map. That means if any oriented n surface is given, we can shift that normal to the origin, and since the norm of each that normal is going to be 1, we are getting a unit circle in the origin. So actually the Gauss map maps the surface S to an n sphere. That is, Gauss map is from S to Sn. Next definition. The image of Gauss map. The image of Gauss map. Let us take this image as n of s. S is a surface. So this means set of all q belongs to Sn such that this q is equal to some n of p for some p belongs to S. This is called the spherical image of the oriented n surface. So what is a spherical image? So it says that whenever having a Gauss map, you consider the set n of s equal to set of all q belongs to Sn. That means from here we are considering this my q here. So you should consider that q belongs to Sn such that this q is equal to some n of p for some p belongs to S. So here is my p. I am shifting here. I am getting a point on the unit sphere. So this is the unit sphere. Elements in the unit sphere will corresponds to our image set of Gauss map. That is, we will say that there is a spherical image. Let us have some example here. So again I am taking R2, and here I have got a surface something like this, and I have got the map as unit normals. I am giving in this direction. Okay, all are going to be unit normals, right? So like that, one orientation I am giving here. So I'm taking a point here P. So this is my axis x1. So here should be my x2 axis or y2. So I should have here okay, let us see how it's coming. Okay, better I should insert one. Okay, so I am having the unit circle here. Now I want to have this direction here. So exactly I will get the points of this side, right? This side I will get, right? Now this will be my, because when you're mapping this to here means exactly I am getting the map like this, right? So like this. So when you're considering the spherical image means you're considering the points on S1 or in Sn. So here I should consider these points. So when I'm considering this point means I'm getting a part of this circle. So my spherical image is like this will come, right? So it's as a part of this circle only we come. So I should, oh, that's a mistake. Okay, now this for n equal to 1, so I should draw it in R2, right? So n equal to 1. For 2 we'll have something like this. Suppose I have got a surface. So it should be in 3D. Suppose my surface is something like this, and I'm giving the direction like this. Okay, so here also want to give the direction. Okay, so like this. So when I'm shifting this into my sphere, okay, suppose this is my unit sphere, then I want to represent unit sphere means it should be in 3 dimensions case, right? So if I'm drawing like this means I will get exactly this portion, right? Now this portion will represent my spherical image because I'm converting this to here. So this is a sphere, right? So I will get this as my sphere. So I will get this part of the sphere as the spherical image. That is, this is my n of s. So this is x2, x3, x1. So like this when n equal to 2. So this is the idea of spherical image. So note 1. The spherical image of an oriented end surface. The spherical image of an oriented end surface as records the set of direction, record the set of directions which occur as normal direction to s, which occur as normal direction to s. Hence its size is a measure of how much the surface curves around in Rn or Rn plus 1. What this means is the spherical image. What is the significance of spherical image? So the spherical image means exactly it will give how this curves around this surface. Okay, so it's actually give how your curve has got some smooth curvature or something like that. So when you are taking a sphere itself means you will get the spherical image as the entire thing, right? So in particular when you are having a compact surface and you are giving an orientation to that, you will get exactly the entire sphere. So that is the note 2. If an end surface is compact, then it must have its spherical image. It must have its spherical image as Sn. So whenever compact means closed and connected one. So whenever it is a closed one means you are giving the orientation to each and every point in that closed space. So whenever you are shifting that to a unit circle, you have to give the direction in all the directions you want to assign the normals. So it may come something like this. Suppose this is an oriented one. So I should give that orientation to each one, right? So like that. Okay. So I am having this direction like this. Each point I should give the direction. So whenever you are shifting this into your R2, so I'll get for each direction I want to make my normal. See, like this will come, right? So each and every point I should have this direction. So exactly I will get a circle like this, right? So this is what saying that whenever a surface is convex, then we must have the spherical image as Sn. So in this section we have covered only two definitions. That is, first definition is what is a Gauss map, and second one was what is a spherical image. Okay, hope you understood these two concepts. The next session we will see a theorem on Gauss map. Okay, thank you.